Let's discuss the first 4 problems from today's Division 1. Problem A. You can read it now or listen to my explanation. In my words, you are given two numbers n, m. You need to construct a matrix of size nm with the given property. If you take any square of size 2 by 2, the ZOR of 4 numbers in the square must be equal to the ZOR of 4 numbers in this square and the ZOR of 4 numbers in this square. And you want to maximize the number of different elements in the matrix. Okay, first of all, let's try to come up with some shape of a matrix that satisfies this condition. I came up with this. If we fix the topmost leftmost square, let's call those numbers a, b, c, d. If we just copy a, b, c, d all over the matrix, no matter which square of size 2 you will take, the ZOR will always be the same. It's ABCD, ZOR of ABCD. So of course, this condition will hold. So we already have 4 different numbers. And now can we make every copy of those ABCD different from the original? Well, yes, if you just ZOR this whole column by some number, and then this whole column by some other number, and then this whole column by some other number, and so on. Of course, the ZOR didn't change. The ZOR in each square of size 2 by 2 didn't change because it was sorted by some x 2 times and by some y 2 times. If you ZOR some number by some x 2 times, those x's will cancel out and the ZOR will not change. This is one of the main properties of this function. We can do the same with rows. Choose a different number for each row and XOR this whole row by one number, this whole row by other number, to make sure that every ZOR of some number assigned to some column and some number assigned to some row, to make sure that every such ZOR is different, let's just allocate the first 32 bits of our 64-bit integer for columns, and the second 32 bits, the second group of 32 bits for rows. And then we can just assign all the possible combinations: 0, 1, 2, 3, and so on for every column and for every row. Now each pair of a number assigned to a column and a number assigned to a row will give a unique ZOR, which means that we can forget about ABCD, set them all to 0. And still, all the elements of the table will be different. So the final solution is just assign a number that uses the largest 32 bits to every column and some number that uses smaller 32 bits to every row. And then each cell is equal to just ZOR of this and that. Every ZOR in every square 2 by 2 will be equal to 0, so the condition of course holds, and all the numbers are different. The implementation is here. Here I just assign I shifted by 32 bits to every row and j to every column. I could write plus here, or I could write ZOR. It doesn't matter because j and I occupy different bits. Now for the second problem B. You can read it now or listen to my explanation. In my words, you are given two sequences of integer numbers of the same length. For each I from 1 to n, you want to cross out the ith element of the first sequence or the ith element of the second sequence. but each sequence must remain non-empty. After that, you take the maximum among the remaining elements of the first sequence and among the remaining elements of the second sequence. The difference of those maximums must be as small as possible. You need to output the minimum distance between the two maximums. Okay, let's first of all format this data. Let's bind those pairs together and rearrange them in such order that the first sequence becomes non-decreasing. Now you can fix an element which you want to be the maximum among the remaining elements of the first sequence. To make sure that this is the maximum among the remaining elements of the first sequence, you want to cross out everything that comes after it. And you can freely choose any subset of those elements that you cross out. You can cross out all of them, you can cross out none of them, it doesn't matter, this will be the maximum. So, if you cross out this, it means that all of those remain. And you are free to choose which of those remain, which means the maximum among the remaining elements of A will be this element, and the maximum among the remaining elements of B will be either maximum on this suffix of B, or some element from this set of elements. We consider two cases. First case is when we want to make the maximum among the remaining elements of B here. It means we can just cross out all the elements here and guarantee that the maximum among the remaining elements of B is equal to the maximum of this suffix. The second case is if we want to make the maximum among the remaining elements of B here. We can further break it into two cases. If the maximal element that we leave here is larger or equal than our element x, let's call it x, the element that we want to be the maximum among the sequence A. Or if the maximal element that we leave here is less than x. If we want to make it larger or equal to x, of course we want to make it as small as possible. So we take the smallest element here that is larger or equal to x and cross out everything else. And then of course we need to check that it is larger or equal than the maximum element here. And in the second case, if the maximum element that we want to leave here is less than x, then of course we want to make it as large as possible to be closer to x to decrease the distance. So in this case we take the largest among those elements, which is less than x, and also check that it is larger or equal to the maximum element here. If it is so, we can also update the answer with such option. Of course, we can pre-calculate all the suffix maximums in OFN. So now we just need to be able to quickly find the smallest element here to the left of this position, I, that is larger or equal to x, and the largest element among those which is less than x. To be able to do so, we can just put those elements into the set as we go. So when we increase I, when we fix this element, we will add this element to the set. In the set, we can use the lower bound to find the smallest element larger or equal to x and the largest element smaller than x. Let's look at the implementation. Here we read it as n pairs, then sort those pairs by the first value, then we pre-calculate maximum suffix. Max suff I is the maximum of the second values on the same I interval from I to n. Then we create a set. This is a set of second values that we have passed. So the set of second values of everything to the left of I. And create the best answer. When we fix I, we use the lower bound to find the smallest element that we left larger or equal than our fixed element, x as I call it. Then I check if such element exists and its value is larger than the maximum on the suffix to the right of I, then I can update the answer with such distance. Then I check if the element I found is not the beginning of the set, then I can subtract the iterator to take the previous element, which of course will be the largest value less than x. I also check that its value is larger than the maximum on the suffix to the right of I, and if it's so, I can also update the answer with such distance. And finally, if there is something to the right of I can also just cross out everything to the left, from the second sequence I mean, and the largest remaining element will be of course this, and I can update the answer with such distance. And then I will move I, so I need to add this second value into the set. And then I output the answer. Now for the problem C, you can read it now or listen to my explanation. In my explanation, we are given n sequences of integer numbers with a total length of no more than 200,000. We need to concatenate them in some order, and in the resulting sequence, in the resulting long sequence, we take the number of elements that are larger than everything to the left of them. We want to maximize the number of such elements. So let's again format the data a little bit. When we have elements like 3, 6, 4, 9, 8, 7, we care only about 3, 6, 9, for example, because those elements, we are sure that there will be never less than all the elements to the left of them. So let's delete them, let's get rid of them. Let's format the data so that in every sequence we leave only such elements that are at least larger than everything to the left of them in their sequence. Now suppose we concatenate the sequences in such order. Of course, all the elements that we left here will count as good elements, as those elements that are greater than everything to the left of them. Then we'll also count some suffix of elements here, those elements that are larger than the last element here. Then it can happen that no elements from here are larger than the last element from here. So the effect of this sequence will be 0. Then, for example, 2 elements from here are larger than the last element from here. And then, for example, no elements from here are again larger than the last element from here. So this sequence will also not affect the answer. But what we can state is that the sequences that do affect the answer, they go in the order of increasing maximum. Because this element is the maximum here. It was larger than this. And this element was larger than that. So we can preliminarily sort the sequences in the order of increasing maximum. After we do so, we might just want to choose the sequences that will affect the answer. Those sequences that were not chosen will be put in the end. They might affect the answer, but we don't care if they do so, because this will not decrease the answer. They will only increase the answer. But let's suppose we fixed those. Of course, we must glue them in this order, in the order of increasing maximum. So now let's first create a process dp, which will not pass the time limit, but this will be at least some solution. Let's consider a process where we jump to some sequence, then from it we jump to some other sequence, to some future sequence, and so on. The price of the first jump is the length of the sequence, because all those elements will be counted as good elements. Then the price of this jump is the number of elements in the sequence that are larger than the largest element here. The price of this jump is the number of elements here that are larger than the last element here. So we want to jump through the sequences to maximize the total price. Such process has n squared transitions in total, because we can jump from any sequence to any of the future sequences. All of n squared to be precise. So of course, we will not consider each transition separately. We will instead try to optimize this approach. Without changing the process, we'll just optimize the calculation. Let's call dp of I the best total price we can reach if we stop at position I. So for example, like this. how can we quickly calculate dp of I? Let's fix the length of the suffix that we want to be counted as good elements. And let's find the best jump such where those elements will be good. Let's call the smallest of them p, for example. So dp of I can be updated with number of those elements. Let's call it len plus maximum among all dp of j, where j is less than I, and maximum elements on sequence j is less than p. So we can jump only from those sequences j for which the last element is less than p, if we want those elements to be good. We can easily find such best dp of j in all log time if we use segment tree. Let's just imagine an auxiliary array B, where for all values from 1 to 200,000 inclusively, on position x, we store the best dp of j such that j is less than I and max j is equal to x. Now to find this, we just need to take maximum on the prefix of array B, prefix up to position p non-inclusively. And when we calculate the dp of I, we just update b of max of I. We can do both operations using the segment tree. Of course, we don't need to store b explicitly, we just store the segment tree by maximum on this array b. And by the way, this number came from the fact that the largest possible element of the sequence is 200,000. If it was larger, we could also solve this problem by just initially compressing all the coordinates and then applying the same solution. Let's look at the implementation now. That's a non-inclusive right border for the range of values. This is the segment tree array. This is set element in the segment tree. This is get maximum on the segment. Here I find the first power of 2, which is at least 2 times max x, to resize the segment tree with that value. Now I read the sequence. When I read the sequence, I push back only those elements that are larger than everything that came before them in that sequence. And B is the array that is needed to sort the sequences in the order of maximal elements. I sort the array B. The initial best answer that I know is 0, if 0 elements are larger than everything that came before them. Now I consider another sequence. Res is actually dp of I, but as I don't need to store it, this will be a local variable. Then I fix the suffix of elements which I want to be good elements, and find the best dp over all sequences that came before and that end on an element less than my current element. And I add the number of elements on that suffix. Here, last is the maximal element on my sequence. I update b of last in the segment tree. I update with the best of two options, the old value and the new value. And I also update the answer with dp of I. And this is the tricky part. After I outputted the answer, I need to clear the segment tree for the next iteration. But if I do it in all of max x, it may result in a time complexity of max x on every test, which may not pass the time limit. So instead, I just clear those values that I've used. So for every element of the sequence x, I set the value of bx back to 0. And now the last problem for today is D. You can read it now or listen to my explanation. In my explanation, you are given a graph of n vertices and m unidirected edges. Each edge has a cost which you need to pay in order to use it. You initially have $p, let's say. But also you can perform any amount of shows in the town which you are currently in. The show in the town I will bring you WI dollars. The question is, what is the minimal amount of shows you need to perform to get from vertex 1 to vertex n, or from town 1 to town n? Let's consider the best answer and try to make some statement about it. Suppose this was the best path. Suppose you perform some shows here. Then you perform some shows here. And then you perform some shows here. I claim that the price of the shows must increase with each new town where you perform. So the price for the show here is larger than here. And here it is larger than here. Because if the price of the show here is larger or equal than the price of the show here, you can just perform as many shows here instead of here, and get the same amount of money but earlier, or the larger amount of money but also earlier, which is always not worse. So let's always consider the answer in such shape. So let's consider the answer only in such shape where we perform a show in a new town only if its price is larger than the last show we performed. So this already allows us to sort the vertices in the order of increasing price of the show. And we know that the shows in which we perform will go in such order. Let's also consider the price of the show here in n to be infinity, so that n is always in the end of this sequence. Because if we arrive into n, we don't need to perform anymore, so it doesn't matter what the price is actually. So the vertex 1 is somewhere in the middle of this sequence, and the vertex n is in the end of this sequence. We might want to perform in town 1 if we want, and then move to some other town. Maybe visiting some other towns as well, but the next town in which we perform will be to the right in this sequence. The next town in which we perform will be again to the right. And finally, we arrive to n. Of course, if we fix the sequence of towns where we want to perform, we will choose the shortest path from here to here, the shortest path from here to here, and the shortest path from here to here. We can pre-calculate all the shortest paths between every pair of vertices using a and Dijkstra's. It will take n times m log n time, which is sufficient for this problem. So now if we fix the sequence where we want to perform, the question is only how many shows do we perform in each town. And I claim that each time we perform just as many shows as we need to just arrive to the next town where we want to perform. Because suppose the minimal number of shows that we want to perform here to arrive to the next town where we want to perform is p. Let's say I perform the p needed shows to get there, and then also e extra shows in this town. I could instead perform those e extra shows here and get more money. So if the initial answer was correct, such updated answer will be also correct. So let's also only consider the answers in such shape where the amount of shows that we perform in the town is the minimal possible amount to get to the next town where we want to perform. So we can again use the process dp with jumps, with such process that jumps from this position to some others and eventually to n. But the price of the jump is not entirely fixed by the endpoints of this jump, because the price of the jump could be the number of shows you need to perform in this town to get to that town. But you could already have some money in your pocket that you saved from the previous shows, even if you didn't want to. First of all, you had some money initially, and the second reason is because the length of this path may be not divisible by the price of the show, so we will have some remainder in our pocket after we perform this many shows and then use this path. But it's still true that if we have two different paths to the same vertex, we want to choose the path which has the smaller amount of shows. Suppose we have performed A shows during the first path, and in the end we have B spare money. And during the second path we performed C shows, and in the end we have D spare money. Now suppose the first path is strictly better than the second, in terms of the number of shows that we need to perform, but strictly worse in terms of the spare money that we have in the end. So A is strictly less than C, but B is strictly less than D. I claim that we can always compensate the lack of money at the end of the first path by just giving one more show in the final town. Because if C is strictly less than A, it means that C is at least 1. Which means that on the final town where we performed the show on the second path, we didn't have enough money to pay for the road. So we had some amount of money and we needed a larger amount. So we started performing shows, gaining, let's say, W money for each show. And then we stopped when we had enough money and paid for the road. So the remainder that we have is less than W. Because if it's larger or equal to W, we didn't have to do the last show. So it means that D is strictly less than W. But the price for a show in this town, let's call it W prime, is at least W. Because we sorted them in order of increasing price. So if we just make one more show in this final town, we have made A plus 1 shows, which is still no more than C. And we got B plus W prime money, which is already larger than D. So we have arrived in a situation which is strictly better than CD. Thus we have proven that we may only consider the paths to a vertex which have the smallest amount of shows, because we can always compensate for the disadvantage of this path later. This idea leads us to such solution. Let's call dp of I a pair of AB, where AB is the information about the best path of the process that leads to vertex I. A is the minimal possible amount of shows we can do to reach I. A is the smallest possible amount of shows we can perform to reach I. And B is the largest possible amount of spare money we can have if we reach I performing A shows. So with the condition that we performed exactly A shows, what is the maximum amount of money we can have when we reach I? And the transitions are very simple. You just transit from I to all the possible j's larger than I. You calculate how many more shows you need to perform to be able to pay for this road, and update dp of j with the new candidate, where you perform A plus some extra shows, and the money that you have is B plus wi times extra shows minus length, where length is the price of the road from I to J. Here is the implementation. This is just Dijkstra starting from vertex ST. Here we read the graph, read W, set the price for the show in the last vertex to be infinity. Run Dijkstra from every vertex. Sort the vertices in order of increasing price. Create the TP array. Find the position of the first vertex in this order. In my code, we store dp of I, where I is the position of vertex in the increasing order, not in the original order. So where is actually the position of the first point in the order of increasing prices? The base state is when we are in the first point, we performed 0 shows, we have P spare money. And then starting from where to the right, we try to transit from point I to all the possible point J to the right of it. V is the original index of the vertex I, 2 is the original index of the vertex J. C is the price of the show in the vertex V. Len is the distance between V and 2. If it's infinite, then it means I can't reach 2, and I skip this transition. Left is the amount of money that are left in my pocket in the best scenario. shows are the extra shows that I need to perform. If I don't have enough money, then I perform this many shows, which is the difference that I lack over C rounded up. Car is the new candidate for dp of G. The number of shows is equal to the number of shows that I already performed plus the extra shows. The amount of money is the amount of money that were left plus shows times C minus the road. If the new candidate has less shows than the best answer we know for J, or it has the same amount of shows but more spare money in the end, then we update the answer for J. Our answer is the number of shows that we need to perform to reach N. N is the last vertex in the order of increasing price. So the answer is dp.back.first, number of shows. If it's larger or equal to infinite, it means that I can't reach this vertex. Otherwise, I output the number of shows. That's it for today. Thank you for watching. I remind you that I give private lessons on competitive programming. If you are interested, contact me on Telegram. Goodbye.